Uh, Here we go. We've finally made it. A whole new kind of numbers. One of the key promises of the Algebra 2 course. Hopefully you'll feel that it delivers today. Everyone who has headphones on or anything like that, please take those off. Fritz. Oh, you might not hear me. Will you tap him? Yeah, thank you, Fritz. Exactly. Let's get started on this. So for this lesson to make sense, it's important that I review some concepts. I'm going to throw the quadratic formula up on the board. That is something that we will prove, kind of like FOIL, and I hate having to use it now before we actually see why it's true. But it's like the x equals negative b over 2a, right? It was really useful for getting a feel for quadratics, and we'll come back and prove it. So don't think that I'm just throwing the quadratic formula up here and it's like, okay, now I just have to believe this. No, I want you to doubt everything I say. I want you to doubt even that. But just give it to me kind of like a cloud. Give it to me like an axiom right now. Just pretend that the quadratic formula works, and several other things. Review. This symbol here. You might not know that symbol. That means for all. A, B, in the set of positive real numbers and 0. Partly, I just want to throw up some fun symbols for everyone to ooh and ah over. This symbol here means for all. Does anybody remember what that symbol means? We've done this one before. I've written it up there. Anybody remember what that means? Oh, Chelsea, will you pull your mask up? Thank you. Yeah. In the set, exactly. In the set. And then this one is supposed to be a U. I want to make it a little more accurate, just this is our first time using it. A little U, it means union. Whoops. Stick with the colors. Which means combine together. Join together, just add all the things in one set to the things in the other set. So put them together. So this is the positive real numbers. And that's just the set containing 0. So we're taking the set containing 0. That's just a brace ending the expression. There we go. So you've got the set that has 0 in it, the set with all the positive real numbers, and you join them together, and you get a set of non-negative real numbers. Okay. Did I say A and B? I don't want to add C in there. Oops. And we'll extend these rules for not just positives at some point, but right now we're just using them for positives. Anybody know what that's equal to? A times B. What can I do with that? I have the square root of a product. You've done this before. The square root of 8 as an example. What can you do with the square root of 8? Do this, square root of 4 times 2, and then what can you do? Yeah, Adam. Okay. Yeah, Alex. Yeah, the square root of 4 times the square root of 2, which is 2 times square root of 2. Right? You could take this step here is what this rule is about. You could go from here to here. Right? This is called simplifying a radical. And you'll get some experience with this as in the next unit. We're not going to do too much of it right now, but it's just something that I want you to remember. You in the geometry curriculum, this is one of the concepts that's covered. You may or may not have seen it yet, but I'm just telling you it's something you can do. This is equal to that. And a good check, if you wanted to think about it, think about the square root of 16. What's the square root of 16? 4. This is not a proof, remember, I'm just doing it with one pair of numbers. But if I wrote the square root of 16 as the square root of 4 times 4, that would be the square root of 4 times the square root of 4. And what's the square root of 4? 2. So we see 2 times 2 is the same as 4. That's not a proof, but it's just kind of helping your intuition see, oh, yeah, I kind of see what's going on there. I see that's making sense, right? What's this question asking? It's saying, what do you multiply by itself to get 4? This is saying, what do you multiply by itself to get 4? And this is saying, what do you multiply by itself to get 16? Well, the things that you'd multiply by itself to get 16 is 2 times 2 to get 4 times 2 times 2 to get 16, right? 4 times 4 is 16. So, like, you know, in other words. And I'm going to erase this now. I just wanted to throw it up there. We'll have another example, and I'll give you a problem to try and do on your own, but I wanted to throw those up there first. Everybody have a second to write that down? Actually, I'll leave it there. Continue. So the square root of A times the square root of B. And then there's another one. Here. You can do the same thing with A over B. And we'll see an example of this one in a moment. You may not have, just judging by people's faces, you may not have seen this in your geometry class. Does anybody remember, did you see that in geometry last year? Okay. So it's not that interesting, but it is something, I guess I'm going to go against what I said, just judging by the head shaking that you hadn't seen it. Consider, for instance, the square root of 1/4. Right? What is the square root of 1/4? 1/2. And Alex, it's 1/2 because what happens? What needs to be true about this thing if it's the square root of 1/4? What should I be able to do 1/4? When I talk about the square root of 16 being 4, what can I do to 4 to get 16? Multiply by itself, right? 4 squared is 16. So 1/2 squared, 1/2 times itself is 1/4. That's why 1/2 is the square root of 1/4. Right? That's what it means. It means find the thing that you multiply by itself to get 1/4. Right? And the thing is 1/2. 1/2 times 1/2. And then you can try using this rule on it. This would turn into the square root of 1 over the square root of 4. And you can kind of get the feel for that. Well, the 1 you didn't even have to worry about when you were thinking about the 1/2. And then you were asking yourself, what do I multiply by itself to get 4? Right? And that's the calculations that you're doing to get this are pretty much the same as the calculations you're doing to get this. Again, that's not a proof of this general statement. It's an argument for why it makes sense. It's an appeal to your intuition. Okay, and then we have the quadratic formula. Ax squared plus bx plus c equals 0. This arrow here means implies x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So these are the three things that we need to know. This quadratic formula says when you have a quadratic equation in standard form, you can use this formula to get the roots, the solutions to that equation. Yeah, Bianca.
Is that like the full version of the equation you use to get the matrix?
Oh, you're noticing the axis of symmetry in there. Does everybody see what Bianca's seeing here? Bianca's noticing negative b over 2a. Right, ignoring this part. That's actually some intuition that if you carry it forward, would allow you, if you knew this was true, right? We don't know the quadratic formula is true yet, you're just pretending it's true. But if you use this, you could actually prove the equation that we have for the axis of symmetry. And it's kind of interesting to think about how you would use this to prove it. What I would recommend doing if you want to try and do that, oh, Alex, I see your hand. Let me go to you before. Are you asking about something over here or on what I was talking about now with Bianca? Okay, so I'll come to you in just a minute, Alex. So if you were trying to make that argument, what I'd recommend doing, just as a hint, is to think about what the implications of the quadratic formula are graphically. Think about what it's telling you graphically, like make a specific example, have a specific parabola in mind drawn in your head on a graph, and see how this implies the thing about the equation of the axis of symmetry. And now you, Alex, sorry.
So if an axiom is wrong, then basically everything else.
So remember how axioms are like clouds. You really can't say that the axiom is wrong. It'd be like saying the cloud isn't there. And it's like, what is a cloud? Well, a cloud is like a concentration of water vapor. There's really water vapor all over our environment. It's just a matter of like whether you want to call it a cloud or not, right? And so we're picking a thing and calling it a cloud. We're saying, here's this cloud. Somebody who doesn't call it a cloud, who doesn't accept that axiom, will end up with a whole different structure built on top of it. The bricks that you use on your structure, the theorems that you prove based on the axioms that you have, those bricks won't sit upon another set of clouds that somebody else has if they don't accept your set of clouds. Now, that's not strictly true. It's possible that you could have two axioms that are different, but that support the same brick, that support the same theorem, right? You just go about proving it in a different way, potentially, but you're kind of getting the feel for what this whole process of building mathematics looks and feels like. The key idea there is those axioms are things that you choose, and right now we're just choosing, I'm asking you at least, to choose to accept that this is true. At some point, I'm going to claim that it's not any longer an axiom. We're going to go back and we're going to say, let's prove this. We can prove it with axioms that we already have. And then it sits on different, then it turns from a cloud to a brick. It becomes something that rests on top of the other clouds that you already have. Okay, but I don't want to get too deep into that. I really want to get to this next part. Thanks for the question. Let me avoid going down too far into it because I'll just keep going. I love that conversation. I want to give everybody a minute to just try to simplify this radical. Now, what does that mean to simplify the radical? Simplifying, in most cases, is a fairly, arbitrary is the wrong word, but it's a convention. It's not like something where you can prove that something is simplified without a clear statement of what the rules are for simplifying. So I'm just going to tell you that what I mean by simplifying this radical is I mean taking this thing and pulling as many factors, as many perfect square factors out of it, identifying perfect square factors, and then using this rule up here to pull them out from underneath the radical. So I want to walk around and see everybody trying to do that. Write 32 as some combination, some product of a perfect square factor and a non-perfect square factor. Here, what's that? So this is 2. So you can rewrite this line right here. It's 2 times the square root of 8. Yeah, don't erase it. Yeah. Oh, you can erase it. Yeah, yeah. That's 2 times the square root of 8. Then, I was asking a lot. So you're talking the square root of 8 is the square root of times 2, the square root of 2, right? But don't lose the 2, right? The 2 is there. That's hard. Oh, I should have had you. Sorry. I wish I could circle this and like drag it over here. Just this part right here. Do you mind rewriting that? It's super annoying, I know, but just I should have put a line down right here. It's my fault for not doing that. I just know what's going to happen with the board. Right here. Yeah, there we go. I'm sorry, I'm going to do this. Okay, everybody look at the work that Annie's doing up here. Try to follow what she's doing. Hey. So, important to see these steps. This is a really important, as I walked around and saw people's work, I saw that a lot of people's work didn't have the kind of feature that I want to point out in Annie's work. each of these equal signs is signifying a really important fact. When she puts this equal sign here, over here, she's not like she's not just writing a part of what's here. She's writing this thing over. She's writing the square root of 32, exactly that, over, but with some sort of modification by using some sort of property. Right? So what did she do to change the square root of 32 to the square root of 8 times 4?
She took all the superfluous roots.
Yeah, but I mean, like, why is this equal sign true? What fact is she using that makes that equal sign true? 8 times 4 equals 32. That's all she used. Right? Now, it's true. Ashley's like, well, she could also have done 2 times. She could have also done 1 times 32 equals 32. Right? But she picked 8 times 4 for a reason. And the reason she picked it is because 4 is a perfect square. But that's one level. There's the other level of why is the equal sign true? And I want everybody to look carefully at your work. In a lot of cases, the work that I see does not have those kind of that chain of equal signs. Now, I'm going to show you another way that you can do this problem. I'm not saying you have to do the problem this way, but the part that I do want you to really practice is, while simplifying, use equal signs and make sure those equal signs have the meaning that you expect them to have. Don't write just part of the thing. This next one, why is this equal sign true? Yeah, Bianca.
Because of the axiom we proved earlier where the square root of 8 can be the square root of 8 and the square root of
So everything you said, spot on. There's one word that she used. Did anybody notice it? What was the one word that she used that I'm like, that word? Axiom is correct, right? The axiom that we what before? Proved. First of all, do you prove an axiom? No. Proving is using axioms to say something is true because of the axiom. Like proving is something you do on top of axioms, right? Axioms, you don't know they're true. You're pretending they're true. We don't know that this is true. We're pretending it's true. We're saying, let's pretend this is true. So say it again, Bianca, just be really careful in your language. Why is this equal sign true?
It's equal because of the axiom that we have.
Yeah, exactly. That we have, that we're assuming, or that we're taking, or that we're using, right? All of those, but you can't say that we proved it, right? Not only do you not prove axioms, but what I did over here with the example, with plugging numbers in, that's not going to generate a proof, right? That's just going to, like, a proof can't be just for some numbers. It needs to be an argument that works for all of the possible numbers. And how many numbers are there? How many numbers is this making an argument for? Hint. How many numbers is this claiming to be true for? Yeah, Sam. All non-negative real numbers, claiming to be true for infinitely many numbers. Right? If I wanted to prove this by showing you with just numbers, I'd have to do infinitely many numbers. That would be a long class. I definitely have to ignore the bells on that one. Right? Okay, and then this equal sign here. What makes this equal sign right here true?
Basically the same thing, it's just like 4 times 2 equals 8.
Thanks, Aaliyah. Right? It's just the same thing. She just wrote this whole thing over. That's what simplifying should always feel like. It's just the same thing, but instead of 8, she wrote 4 times 2. And 4 times 2 is 8. Okay, what about this equal sign? Other than Bianca, why is this equal sign true? Yeah.
It's the same thing.
The same thing as this equals sign up here, but what is she using to go from here to here? Yeah, but she's using something that we've already used before. Like, just simplifying it more doesn't tell me, like this is complicated. This is simplified more than this is. But the equal sign isn't true. Right? If I'm trying to simplify this, I can't just write x because it's simpler. Right? I have to have a reason. I have to do something to this thing over here. Right? So what's the argument that we can make that says I'm allowed to do? First of all, what changed from this expression to this expression? The 4 and 2 are separated in their own, it's called radicals, under their own radicals. Right? The 4 and 2 are separate. What allows me to do that? Yeah, Adam. The axiom. This axiom up here says that when you have a product under a radical, you can turn it into a product of the radicals. Right? If this is true, what does that even mean? We're assuming it's true. Right? So, given this axiom, we can do this equal sign right here. We're turning a product, 4 times 2, a radical of a product, square root of a product, into a square root of the first term times the square root of the second. And then why the times square root of 4? Because that's exactly the same line as she wrote here. You can't leave out, that's one of the kind of mistakes or notational errors that I saw in a lot of people's work. They just left that out. You can't just leave that out. You need to rewrite this whole line. Okay, and what about this equal sign here? Why is this equal sign true? Yeah, Adam. There we go. Right? That key word is, the square root of 4 is 2. She just rewrote this line here, but in place of the square root of 4, she wrote 2. Over here, the square root of 4, she wrote 2. Okay, why is this equal sign true? Yeah, Sam. I'll wait on this equal sign. Yeah, what's your question?
The first one, going from 30 to 32, with 4 times 8 times 4. What has to be done?
What allows you to say that 8 times 4 is the same as 32? That's actually, a pretty interesting question. Like, how do we want to, how does multiplication work? Right? It's kind of about what multiplication is, and this equal sign is true because 32 is 8 times 4. And you're asking, why is that equal sign true? And it's an interesting question, but it's kind of actually, even though it seems like, oh, that's really simple, it's actually beyond the scope of what we're doing here. So we're just kind of assuming how multiplication works.
Oh no, I meant, how do you know that root 32 equals
Because 32 is the same as 8 times 4.
Oh.
Right? This here means that anywhere you see a 32, if this is true, it means anywhere you have a 32, instead of the 32, you could put 8 times 4. They're kind of the same thing. That's what the equation means there, is that I could just take this, I could erase the 32 and put 8 times 4 right there. And that's what she's done here. That's what this equal sign is showing. I'm going to take that 32, and instead of that, I'm going to put 8 times 4. Right? Thanks for asking that. That is allowing me to make my point more clearly, right? Every one of these equal signs is doing something just like that. Right? She's taking the 32, instead of 32, she's writing 8 times 4. Why can you do that? Because of that. Okay, now we're down to the last equal sign. Why could she do that? Why is 2 times the square root of 2 times 2 the same as 4 times the square root of 2?
You put the index as the like term and then the radical number still there.
That was 3 voices. I want to hear all 3 of you. It was Ashley and who else was talking? Ashley and Chelsea? Was it you, Chelsea, who also talked? What? Will you say what you were saying? Because 2 times 2 equals 4. Okay? And what were you saying, Ashley?
Well, I was just saying it as like 2 times 2 is the index, and then you have the radical numbers for it.
Okay. Yeah, you were saying the same thing, but just with kind of some of the fancy language here, like using the radical word here. We're going to talk about indexes later, and it is important to know. Nobody else looked, just Ashley, so she raised the word. This is not the same thing. So this would be the 4th root of 2, where 4 is the index. This is 4 times the square root of 2. There's actually a times in there that's just implied.
Is there a word for that, though?
There isn't a word for the 4, just coefficient. 4 is a coefficient of the radical as opposed to an index. So those look really similar, but they're really different. I'm going to erase it now. We'll talk about that later. Okay. So we got to this. That was a lot, right, that's hidden in here in the notation. Imagine that you existed, that you lived in a time where we did not have all of this notation and you had to write this out in sentences. Like, how many sentences are in this, like, I don't even know, 1, 2, 3, 4, 5, 6 steps? There's got to be, like, at least 6 sentences, because each one of those equal signs is a sentence, but some of them are going to be longer than a sentence. Like, you're going to have a whole paragraph for this argument that Annie made here. And I'm going to continue to get more and more kind of picky about your notation. Because in mathematics, it's not just arbitrary. Like, this notation is a bunch of sentences. It's like a shorthand way to write out all those sentences. And the same way your English teacher needs to critique your grammar at times, I need to do the same. Like, even if you get to the right answer, if your argument is using incorrect grammar, that's a metaphor, if it's not a correct argument, then there's still a mistake that's deserving of feedback, whether it's losing points on the test or just getting a comment. Okay. Alternatively, another way to do this problem, instead of the square root of 32 going to this, I saw on a bunch of people's work that they approached this a different way. They saw something else in the 32. Yeah, Adam. 2 and 16. Adam saw a 16 and a 2 in there. 16 times 2. Why is that equal sign true? Because 16 times 2 is 32. Okay? What's the next thing after this equal sign that I'm going to write? Yeah, Adam.
Square root of 16 times square root of 2.
Why is that equal sign true? Because of this axiom right here, right? That says when you have a square root of a product, you can turn it into a square root of the first term times the square root of the second term. What's the last line?
4 times square root of 2.
Why is that equal sign true? Well said. That was Rachel. Yeah, thanks, Rachel. Yeah, because the square root of 16 is 4. I'm just simplifying the square root of 16 to 4. Because 4 times 4, 4 squared is 16, right? So that's why I can write 4 in place. And then I just wrote down the whole rest of the line with the root 2. Okay. For those looking forward to seeing complex numbers, I want to just clarify the lesson plan. I'm not going to kind of force it. This problem that we've set up, or that I'm about to set up for you, is too important for me to squeeze it in. So I'm going to give you time to think about this problem, and we'll finish this lesson tomorrow. We still have 12 minutes left, so I'm not done. I just don't want you to be disappointed when we don't get to the complex numbers. X squared plus 4x plus 1 equals 0. So now I don't have to worry about board space also. X squared plus 4x plus 1 equals 0. If I'm trying to solve this, I was trying to solve that. What would I do to solve that? I could try and factor it, and that would be a fun approach. Yeah, Rodolfo. I could use this thing right here, right? It's just in this format, right? It's a line that looks just like this. I forgot to write this here. This arrow, we've used it before, but I want to really call attention to it. What this arrow means is that if this is true, then this is true. It's a way of that if-then language, right? If I turn this into a sentence, this arrow is saying if ax squared plus bx plus c equals 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Right? If this, then this. It's red implies. That's what that arrow means right there, this arrow. The left-hand side, if that's true, then this is true. That's what implies means. Ax squared plus bx plus c equals 0 implies that x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So now I can use it on this. What's my a, b, and c? B is, and C is. So X is negative B. I recommend writing out the formula every time you use it until you're so confident that it's just like basically in your blood. So now I'm going to plug in place of the B, the 4. In place of the B, the 4. In place of the A, 1. In place of the C, 1. All over 2 times 1. Okay, and then this equals sign, I'm going to rewrite this entire thing, but I'm going to do some simplifying. What do I write instead of 4 squared? Why can I do that? Because 4 squared is 16. What do I write instead of 4 times 1 times 1? Just 4. Because 4 times 1 times 1 is 4. And then in the denominator, and then I rewrite the entire expression again, this equals sign. Remember, I'm simplifying. Rewrite the entire expression again. Negative 4 plus or minus the square root. And underneath the square root, instead of writing 16 minus 4, I'm going to write 12. And in the denominator, I have my 2 still. Okay, why is this equal sign true? (16 minus 4 is 12). Okay. Can I simplify the square root of 12? Using this axiom, right? What am I going to turn 12 into? 4 times 3 to pull that largest perfect square factor out. Okay, why is this equal sign true? Because 4 times 3 is 12. Okay, and now? times over. There we go. And why is this equal sign true? Because of the first axiom. Okay, and now what's the next line? -4 plus or minus 2, right? Instead of the square root of 4, thanks. Now what can I do? Cancel out the 2's, right? It's a little weird here to think about, but this -4 plus or minus 2 root 3, this is equivalent to these two things, right? This is equivalent to -4 plus 2 root 3 over 2, or -4 minus 2 root 3 over 2. Look at this one. What can I do with those 2's? Right? Dividing by 2 is the same as multiplying by 1/2. I can distribute that dividing by 2 to both terms, and what do I get? -2 plus root 3. Okay, down here, what would I get? -2 minus root 3. Right? Distributing that 1/2 to both of the terms. -4 times 1/2 is -2. -2 root 3 times 1/2 is -root 3. Now look at those. Look at those together. We've got an or statement between both of those. What's that the same as? -2 plus or minus root 3. Right? So really, I could have kind of skipped this part in the middle and gone directly from here to here. This plus or minus works with the distributive property the same way in the top expression and the bottom expression. Whether it's a plus or a minus, you're going to be able to distribute the 1/2 the same way to get to -2 plus or minus root 3. In the future, you wouldn't write this part right here. Like, this would be like stuff you wouldn't have to write in the future. You just go directly from here to here. This is kind of showing why the equal sign is true that I left out. Kind of like, I meant that to be both bars of the equal sign, but now I don't have space. I'll do it like that. There we go. Okay. Yeah, Ashley.
I have a question. So, in the first part, you can see that there's a square. Can you just cancel out the square in the beginning?
Over here.
When you plug it into the quadratic formula.
Right here.
Mm-hmm.
This, cancel it with what? Oh, with the square root.
Mm-hmm.
Does that work? Essentially, you're asking that, right? Because think of this is, let me write it this way, 2 squared plus 2 squared. Like, can I cancel the squared with the square root? That would turn into 2 plus 2, right? Is 4 the same as this? No, because 4 plus 4 is 8. The square root of 8 is not 4, right? This step here is not valid. You can't do that. This kind of axiom, well, I shouldn't say you can't do that. The axiom that we've implicitly assumed that we're using when we're doing our calculations, the way our numbers work, we are not assuming this axiom here. If you assume this axiom, you end up with numbers that behave very, very different from what you're used to. Like, you'd get that the square root of 8 is 4, and that would be really weird. You'd have a whole different kind of numbers would behave in a very, very different way. So we do not accept this axiom, or we don't assume this axiom. Okay. What I did want to do in the last 2 minutes is I wanted to just kind of check and confirm that this thing works. That this -2 plus root 3 or -2 minus root 3 actually solves this equation, right? That's the claim, that solves that. So I should be able to put that in there. -2 plus root 3, I should be able to plug that in, squared, plus 4 times -2 plus root 3 plus 1, and I should get 0, right? This is my check, right? I'm just taking this value that I got that's equal to x, and I'm plugging it in for x to see if it actually did solve this equation. How do I square that? Well, I need to FOIL it. Distribute my 4 here. 4 times -2 is -8. 4 times root 3 is 4 root 3 plus 1. Question mark equals 0. I'm checking to see if those are equal. Okay, FOILing this. First term, 4. Outer terms, -2 root 3. Inner terms, -2 root 3. That's -4 root 3. Last terms, what's root 3 times root 3? That would be root 9, which is 3. Minus 8 plus 4 root 3 plus 1 equals 0. 4 plus 3 is 7. Wait, well, what happened to these guys? They cancel. 4 plus 3 is 7, plus 1 is 8. Minus 8 is 0. I get 0 equals 0. It does work. I shouldn't have equal signs there. And I want to explain that more, but we're 6 seconds over. There is the bell. The bells are 9 seconds late. Have an excellent day. Enjoy the rest of your day. And I will pose the fun problem tomorrow at the start of class.